Now I'm going to shift gears and talk about the generation of multiple rather than single 3D conformers. The primary use of this functionality in ADMET Predictor is for 3D virtual screening. The idea is to take a set of compounds, probably a large set, such as those from a commercial vendor catalog, and use it to generate a 3D conformer database. You can then take one or more 3D query conformers and quickly screen that conformer database to find similar structures. Those similar structures would then be worth considering for purchase and follow-up in vitro testing. All right, I'm just quickly going to borrow a slide from the ADMET Predictor release webinar for version 11, where we introduced this virtual screening functionality. So the similarity scores consist of a shape term based on overlap volume, and optionally a feature term based on the alignment of pharmacophore features. And then users can adjust the relative weights of those two terms. The overlap volume is computed using atom-centered Gaussians. This approximates the exact hard sphere overlap, but is faster and more convenient for optimization. So given a query conformer and a database conformer, for each of several starting alignments, BFGS optimization is used to find the rigid alignment that maximizes the similarity score. This is showing sort of the interface for visualizing the pharmacophore features that you define. I'll show this in a few minutes. And then there's a link here to a paper that describes the underlying mathematics behind the similarity scoring. I believe this is very similar to what's used in a lot of other commercial tools that have similar functionality for 3D shape and pharmacophore similarity screening. Now for this training video, I've already built a 3D conformer database, but I want to just quickly show how it's done. So under the library menu, under 3D, there's an option Create. So here you would choose a structure file. This could be an SD file or a SMILES file, and then an empty folder to hold the resulting database. There are options here to use existing 3D conformers in the SD file instead of generating those conformers on the fly. And there's an option to append conformers to an existing 3D database that you've already created. If I click the 3D conformer options button, it will show the same settings page that we saw earlier in the video. Note that now the option for multiple conformers is turned on automatically. The next options are the maximum number of final conformers for each compound, set to 100 by default, the minimum RMSD between conformer pairs, so that's to ensure diversity, and then the maximum energy range among all conformers in kcals per mole. When this maximize diversity option is checked, high structural diversity among the conformers will be prioritized over lower energy values. And then finally, there's an option to control the extent of the search over torsion angles during conformer generation. Again, the ADMET Predictor user manual has more information about these parameters and the overall 3D methodology in general. Now, creating the database can be time-consuming, but the idea is that you pay that cost just once, and then you can screen the database over and over again with different queries, and each individual screen is much, much faster. So I'm not going to create the database right now. I just want to quickly show what it looks like on disk. So I have one here for a collection of compounds from the Kemble database. And if I open that folder, the database essentially consists of a set of binary files. Each one represents on the order of 1 million 3D conformers. So the size of this database in total is about 8 million 3D conformers. The files themselves are independent, so you could distribute them among multiple machines to make the subsequent screening even faster. Now, to illustrate the screening process, I'll open up another SD file that has a single 3D conformer in it. I've chosen one here. So this is an actual drug called L-trombopag, used to treat thrombocytopenia. Now you can see from the geometry column that 3D coordinates were already contained in the SD file, and they've now been loaded into ADMET Predictor. As I mentioned before, you can perform a similarity screen using more than one query compound simultaneously. But for simplicity, in this video, I'm going to use just the one here. So to initiate a database screen, you would use the menu item Library, 3D, Search by Similarity. Okay, the first step is to choose the database to screen against. So I'm going to browse to that Kemble database that I was showing earlier. Select that. Okay. Once you've selected that, the boxes here will show you the number of total compounds and total conformers that are contained in that database. So it's 100,000 and just over 7.5 million, respectively. You then choose a folder for storing the results. So I'll choose an empty folder here that I've set up called results. Okay, so I just want to briefly highlight a few of the other options. For purposes of the volume overlap calculations, you can choose to treat all atoms as though they were carbon. It turns out this simplifies the similarity formulas and results in a significantly faster search with relatively small differences in the resulting similarity scores. Running on a compatible NVIDIA GPU provides an enormous speed up, as much as 2 orders of magnitude in our testing. The machine I'm using here does have a decent GPU, so I'll leave that on as well. The feature weight controls the importance of the pharmacophore feature alignment term relative to the volume overlap term. I'm going to leave this as 0 for our first run, which means that only volume overlap will be considered. And I'll come back to this in a few minutes. The similarity threshold controls how similar the query has to be to a database conformer in order for optimal alignment information to be saved to the result folder. Now, the raw similarity scores are always saved, regardless of how low they are. But the alignment information takes up some amount of disk space. So the threshold here can be used to ensure that only the high similarity hits are saved to the disk. This is a Tanimoto score, so values closer to 1 indicate greater similarity. And I'm going to change the value from 0.75 to 0.85 for this run. Okay, I'm just going to leave the other options at their default values for this first run. So I think this is now set up, so I'm going to run it. Again, it's running on the GPU, so it takes on the order of 10 seconds or so for these 7.5 million conformers. So it's quite fast. And again, you do have the option of distributing those database files across a cluster of GPU-enabled machines to make it even faster. Okay, a separate ADMET predictor opens up containing the database compounds whose similarity to the query is at least as high as our 0.85 Tanimoto threshold. The similarity scores are provided in a separate column. And just to be clear, the similarity score for a given database compound is the maximum similarity among all the conformers for that compound that were stored in the database. So in our case, that's as many as 100 conformers. Okay, I'm going to sort by descending similarity. So the highest similarity hits are now shown at the top. I drag this over, you can see that the first 2 compounds have almost perfect similarity. They're actually, practically exact copies of our query compound. It looks like they are ionized forms. So the carboxylic acid is ionized. I think one of these has a defined cis-trans stereochemistry at this double bond, whereas the other one does not. So they're 2 distinct compounds. The third compound has a fairly different scaffold relative to the query. Now, in order to see the alignment between this database hit and the original query, there's a link in the spreadsheet to an SD file that stores that information. Now, I have linked SD files to this Biovia tool for 3D visualization, so that will allow me to show the alignment graphically. And this is what it looks like. So immediately, you can see that despite the different chemistries, the overall shapes of the two compounds are actually quite similar. Now, the alignment of the functional groups is not so good, and that's an indication of the fact that we need to incorporate the feature term in addition to just the volume overlap term. Okay, so that's something that we can do next. So I'm going to close this window as well as this initial results window for our first similarity screen. And I'm going to relaunch the similarity search with the query compound. So the first thing I want to talk about are the features. There's already an entry for this box here, which says the input file containing feature definitions. So this points to a file that we distribute with ADMET Predictor. It has a few default features that we provide. You're able to edit this file by using Daylight Smart's syntax. You can define your own features. I've modified the file myself to eliminate some of the features and keep just 3 of them. And I can click this button. This will bring up the window that I showed in the slide earlier. So there's only 3 features here, hydrogen bond acceptors, donors, and rings. And here you can see them superimposed on the 2D representation of the query compound that we're using. So again, the users can modify the file or create a new file. So there's quite a bit of flexibility there. In order to trigger the use of those features, you need to enter a non-zero value for the weighting of the feature term relative to the volume term. So I'm going to set a value here of 4. Now, the reason I chose that is that it tends to put sort of the weighting of the features on an equal footing with the shape. Remember, the shape term uses all of the atoms in the compounds, and typically there would be fewer pharmacophore features than there are total atoms. So using a weighting significantly greater than 1, will tend to help balance that out a bit. Another thing I'll do is lower the similarity threshold from 0.85 to 0.65. Now that's because the resulting similarity scores when using the feature term tend to be lower. And that I think is because you have a lot of situations in which a feature from your query compound is just not going to have an equivalent match to a given compound in the 3D conformer database. And so the overall scores just tend to be lower. So it's good to lower that value as well. I did mention that all of the raw similarity scores are going to be saved regardless of what this value is. This is just for saving the best alignments in those individual SD files that I showed earlier. And then the final thing that I'll do, there's an option here to provide some user-defined queries that will immediately reject compounds from the 3D conformer database, so they won't even be considered for screening. So I've defined such a file, and I'm going to point to it. It's called excludedmotifs.cqf, and I can click a button here to view that file. And there's just one query in it, and it represents 2 ring atoms at the beginning and end here, connected by a 2-atom linker chain. And that's exactly the motif that's shown here between these 2 rings. And doing this is just a way to ensure that you get some unique hits, things that don't look very similar to what you're starting with. And that's often what you're really aiming to do, is to find things that are not obvious, that have a really different chemical structure. So that's the one query that I'm going to use to eliminate some of the hits that I would otherwise get. Okay, so with these options, I did not change the result folder. So when I click OK, it's going to warn me that the previous results are going to be overwritten, which is okay. The screen is going to take just a little bit longer because of the more complicated similarity definition. It now has two terms instead of one, but it's still very fast. We'll open up the window. Again, I'll sort by similarity like before. And, now, you don't have any very, very similar hits, and that's by virtue of that filter query that we used. So even the first compound, it looks a bit different, with the fused ring system here. And I'll just, use this as the first example to show what the overlay looks like. And that's going to bring up Discovery Studio. And now what we'll see is that not just the overall shape, but the alignment of the pharmacophore features is also much, much better. Now you can see the ring systems aligned, and then some of the H-bond acceptors as well are much better aligned here. So this is a fairly compelling example of similarity, despite the differences in the overall topology of the two compounds. I'll just show one other example. Let's see, I think this one here has, again, a fused ring system, but the linkers are different here. You can see the additional nitrogen here. We'll just see what that looks like in the viewer. Okay, so you can definitely see some difference there where the linkers are different, but still pretty good similarity, both in terms of the volume overlap and then the pharmacophore feature overlap as well. So here you got the sulfonyl group aligning with the carboxylic acid. Okay, that was a quick overview of the main 3D functionality available in ADMET Predictor. Again, this functionality is free with any paid property prediction license. So we hope that you will take advantage of it. As always, please reach out to us with any questions or any feedback. Thank you all for joining today, and I will see you next time.